Hello everybody, my name is Stephen Quick. I am a graduate student in the Master of Environmental Studies program at the Evergreen State College in Olympia, Washington. And today I'd like to talk to you about the effects of tree size on sap flow for two common native tree species in the Northwest, that's bigleaf maple and Douglas fir. But today I'm going to zero in on a semi-urban temperate rainforest in Puget Sound, Washington. So my project began with this seed paper written by Georgianne Moore et al., where they compare the controls on transpiration between a young versus an old forest. Now, this paper was written in 2004, and many of its supporting papers were written less than 10 years prior. And this collection of studies represents some of the most recent research that's been conducted on transpiration for native species in the Northwest. And so it presents a pretty significant knowledge gap where we aren't necessarily certain that these conclusions are consistent across time. And the majority of these studies were also conducted at the H.J. Andrews Forest in Oregon, and so we're not certain if these conclusions are consistent across space either. And so my project begins kind of from the conclusions of the Moore study with their key takeaways, which were: one, that young trees were more responsive than mature trees to climatic variability; two, angiosperms comprised an increasing proportion of water use over the growing season; and three, differences in sap flux density were greater between age groups compared to between species. And in that paper, they also talk about some relationships between sap flux density and climatic variables like vapor pressure deficit. And VPD has an interesting seasonality in the Northwest that made us wonder if seasonality affected these outcomes. And so we set out to repeat the study, not necessarily replicate it, but we had a couple key modifications. One was that I was interested in size, and size is often used as a proxy for age, but I think Moore, although she was looking at age, was actually interested in size, so I think she used it as the reverse proxy. So we're more or less getting at the same question here. And then two was that we used average vapor pressure deficit to represent seasonality in the Northwest, and I can help us visualize that here on the right. I have temperature, VPD, relative humidity, and precipitation plotted over time. And I use temperature and relative humidity to calculate VPD, so there is correlation there, but I show all three because I wanted to show kind of the relationship with precipitation and sort of our general climate. I plotted precipitation to show a seemingly inverse relationship, which I think makes the Northwest unique in that our VPD in the fall and winter is low when the air is cold and wet, and then VPD in the spring and summer is high when the air is hot and dry. And so all of this kind of leads up to my research question, and very likely a large part of my thesis, which is: does tree diameter interact with vapor pressure deficit to influence sap flux density for bigleaf maple or Douglas fir? Sorry, that should say sap flux dynamics. So a little bit of background about the project and the team before we go forward. The sites are located at our research sites are located at the Evergreen State College in Olympia, Washington. We have partners at the Washington State University Puyallup Research and Extension Center, and they're developing some modified methods that address some accessibility concerns in urban environments, and I'll get at those here in a second. And then we have funding and in-kind support provided by the Department of Ecology and the Department of Natural Resources. And ultimately, we're interested in looking at the way that trees move water, but today I'm going to be talking about the way that it's moving water through, or trees move water through their stem and through their leaf surface. And I investigated this using the Granier method, which was developed by a French scientist in 1985, and it involves using or installing two probes vertically in a tree stem and delivering a small amount of voltage to that upper probe to ensure that there's always a heat difference. And theoretically, as water travels up through the stem, it cools both probes, and then every 15 seconds we capture the temperature difference, we apply some calculus, and we get sap flux density and the total volume of water that travels between those 2 points in that 15 seconds. And from there, we're able to calculate minute averages, hourly averages, daily averages, and in some cases, seasonal averages. But to get at the accessibility issue here, each one of these sensors is connected to up to 100 feet of cable. And on the other end of that really long cable is a semi-permanent fixed data logging station. This station requires constant access to power. And so you'd be hard-pressed to find anywhere in an urban environment where you can install this system and reach an appropriate sample size of trees without installing more systems. And so our partners over at Wazoo have developed a miniaturized version of this method that you can deploy for a fraction of the time and still come within a high degree of accuracy. So our data will be not only doubled in the next coming months, but also compared to the data from the experimental sites using that modified methodology. And then we also have a picture of our trusty weather station where we collect many different variables, but this is how I calculate vapor pressure deficit. So it's a local, calculated from very local measurements. So getting into the data here, I have sap flux density, total sap flux, leaf specific sap flux, daily VPD, and daily precipitation plotted over time. And the red line is going to show big leaf maple. That bluish green line is going to show Douglas fir, and then that blue line in VPD, daily VPD, is just the trending average. And the importance of those top three graphs is going to depend on your interests or your background. And that first graph is going to get at the core, the physiologic differences in the rate of water moving through the tree stems. And our observations agree with what was observed in the Moore study. There was greater significance, greater difference between age groups than between species. And this graph is showing virtually no difference during the growing season. However, there was some interesting activity in the shoulder season before and after the growing season that where Douglas fir transpired water faster than big leaf maple. And then if we jump down to that leaf-specific sap flux graph, this is also showing us a physiologic difference in the way that the trees move water. What we're seeing here is that big leaf maple moved water a lot faster through its leaf surface compared to Douglas fir, or in other words, Douglas fir is more conservative. And we think that that's an artifact of stomatal conductance because we know that Douglas fir has a greater degree of stomatal control compared to big leaf maple. And then if we jump up to the total sap flux graph, this graph might be more interesting if you're an urban forester or a municipal planner or a planting manager, because it's going to get at the core difference in the total volume transpired by either species. And during the growing season, we see a significantly more water transpired by big leaf maple. But before you're too quick to conclude that big leaf maple is just better altogether at diverting water, I'd like to draw your attention to the sap flux density graph and the VPD graph. And first I'll acknowledge, again, this seemingly inverse relationship where as it starts to rain in the northwest, our VPD falls. And this corresponds to that shoulder activity where we see Douglas fir exceed the rate of stem velocity in big leaf maple. You'll also notice that when big leaf maple is at its peak water flow for any of these variables, there is actually virtually no rain for us in the northwest. So this suggests that Douglas fir might be contributing more to stormwater diversion than big leaf maple. And if we explore this relationship a little bit closer, we see that Douglas fir does in fact transpire water faster through its stem up till about 0.4 to 0.5 kilopascals. And if we look at a distribution of VPD across the whole year, that is about the median value. And so we saw that as pretty validating for investigating these two species. We're hoping to make some generalizations about the species assemblages. So finally, to answer my research question, I only used data from 2023 between May and December. And I plotted mean sap flux, which again is just the total volume of water against diameter to see the effective size. And I saw a significant result for significant result for big leaf maple of size, no significant result for Douglas fir, but there was an interaction between size and vapor pressure deficit for Douglas fir. Basically what this is telling us is that it doesn't really matter what season it is, a certain tree of a certain size is going to transpire a certain volume of water for big leaf maple, but for Douglas fir that really does matter. We think that this is an artifact, as I said, of stomatal conductance. We'll include some data in our final analysis for that. But it might also be an artifact of pathogen infestation in our sites, which we will also verify in the coming months. But what we observed was that the middle-aged or the mid-sized trees were in fact transpiring, Douglas firs rather, were transpiring water faster, or higher volume of water than older trees. And we can kind of confirm the stomatal conductance theory with this leaf-specific sap flux graph. It looks like we saw a significant effect for big leaf maple, but I think the variation there disallowed for a significant statistical result. So there was no effect of size on big leaf maple for leaf-specific sap flux. There was also no effect of size for Douglas fir on leaf-specific sap flux. However, there was an interaction between size and vapor pressure deficit, again, for Douglas fir. So this is kind of a similar result. There is too much variability in the leaf-specific sap flux to say that size matters for big leaf maple. But for Douglas fir, it still does. It doesn't matter if we're not considering season, but the size, different sized trees do transpire significantly different amounts of water given the season. And again, what we observed were that the middle-aged tree or the middle-sized trees were transpiring water faster through their leaf surface than older trees. And then for sap flux density, just the rate of movement through the tree stem, we saw no effect of size of diameter for either species, but there was a significant interaction for Douglas fir between diameter and vapor pressure deficit. This, again, might be stomatal conductance. It might be pathogen infestation. Yeah, in any case, here are some statistical results. I realize my video is covering some of them. I apologize. But this data set is going to double over the next coming months, and then I'll reconduct these analyses and see if they're consistent between years, and then I will compare that to the data from our experimental sites that use the modified methodology from our partners at Wazoo. So this is a virtual presentation, so I will not be taking questions. Thank you. Have a great day.